So, when an AI faces a really tough problem, how does it actually think its way to a solution? I mean, it's not magic, right? It's a process. And today, we're going to pull back the curtain on the core strategies that power artificial intelligence, starting right from the very beginning. Seriously, think about it for a second. Are you the type to just pick a wall and follow it, kind of hoping for the best? Or do you try to methodically map out every single turn from where you started? Well, believe it or not, that very first decision you'd make, that's almost exactly how the most basic AIs start their own search for an answer. We're basically going to follow an AI's education. We'll start with one that's just fumbling around completely in the dark, then we'll give it a compass. After that, we'll see what happens when we throw it into a competitive game like chess. And finally, we'll look at how it learns to solve problems using the same principles as evolution itself. Okay, so our journey begins right here with the simplest possible approach. It's called uninformed search, or as I like to call it, blind search. Let's go back to that maze. You're in there with no map, no compass, nothing. You literally have no idea if turning left is getting you closer to the exit or just deeper into the maze. That's what it's like for this AI. All it knows are the absolute basics. Here's where I start, here's what the goal looks like, and these are the moves I can make. It's just pure, methodical trial and error. So how does a blind AI even explore? Well, it has two main strategies, and you can think of them as having two totally different personalities. First up is breadth first search, or BFS. This is the cautious, careful explorer. It checks every path one step away, then every path two steps away, and so on. It's guaranteed to find the shortest way out, but man, it can be slow. Then you've got depth first search, or DFS. This is the impatient adventurer. It just picks one path and runs down it as far as it can go. If it hits a dead end, it backtracks and tries another long path. It's much, much faster, but it might take you on some wild, scenic route when a shortcut was just one turn away. And this blind approach, as simple as it sounds, is absolutely fundamental to so much technology. It's the same basic logic a web crawler uses to find every single page on the internet. It's how a simple robot vacuum explores a room. This is the bedrock of AI problem solving, and it's kind of hiding in plain sight. Okay, so blind searching works, but let's be honest, it's brute force. It's not very efficient. So what's the next step? Well, we give our AI a little hint, a guiding light, a compass, to help it find its way out of the maze. And this is where the AI starts to get genuinely smart. We're now in the world of informed search, and the key ingredient here is something called a heuristic. Now, that's just a fancy word for an educated guess or a rule of thumb. In our maze, a compass would be the perfect heuristic. It doesn't give you a step-by-step map, but because it's always pointing toward the goal, it helps the AI make much, much smarter decisions at every single turn. And when we talk about informed search, there is one algorithm that is the undisputed star of the show. It's called A-star. And yet, the name is pretty fitting. It is so effective and so versatile that it's become the gold standard, and it's used in tons of applications you probably use every single day. So what's the secret sauce behind A-star? It's actually really elegant. At every single choice point, it does two things. First, it looks backward and calculates the cost of the path it's already traveled. Second, it looks forward and uses its heuristic, that educated guess, to estimate the cost to get to the goal. Then it just adds those two numbers together. And its entire strategy is to always explore the path with the lowest total estimated cost first. The genius of it is how it perfectly balances what it knows from the past with its best guess about the future. And this isn't just theory, this is everywhere. That A-star thinking is exactly what your GPS app is doing to find the fastest route through traffic. It's what advanced AIs and video games use to outmaneuver you, and it's how big logistics companies optimize their delivery routes to save time and fuel. It is smart, efficient problem solving in action. Okay, so our AI is getting pretty good at solving a static puzzle, but what happens when the puzzle starts fighting back? This brings us into the realm of adversarial search. This is a whole different ballgame, designed for things like chess or checkers, zero-sum games where for you to win, your opponent has to lose. The maze isn't empty anymore. Now there's a minotaur in there, and it's actively trying to trap you. The AI can't just find a good path anymore. It has to find a path that anticipates what an intelligent opponent is going to do to stop it. The classic strategy here is an amazing algorithm called Minimax. The idea is pretty straightforward. The AI is the maximizer. Its goal is to make moves that lead to the highest possible score. And it assumes its opponent is the minimizer. Their goal is to always make the move that forces the lowest possible score for the AI. And here is the core assumption that makes Minimax so powerful. It's basically a professional pessimist. It always assumes that its opponent is a grandmaster who is going to make the absolute best, most crushing move possible against it. So the AI's goal is to choose the move that gives it the best possible outcome in the absolute worst-case scenario. It's all about planning for a perfect opponent.
And this kind of thinking goes way beyond just board games. This is the foundation of game theory, which is used to model everything from economic competition between companies to strategic political negotiations. It is the fundamental logic of strategy.
So far, everything we've talked about has been about finding a single, perfect path to a solution. But what do you do with problems that are so complex, so massive, that there is no single path? Well, for that, we need a totally different approach, one that's inspired by billions of years of trial and error here on Earth. Welcome to the wild world of genetic algorithms. And with these, we pretty much throw the entire rulebook out the window. Forget searching one path at a time. Instead, the AI creates an entire population of potential solutions. We're talking hundreds, even thousands of them. Now, at first, most of them are total junk, but a few might have a tiny little spark of a good idea. And that's where the AI stops acting like a navigator and starts acting a lot more like Mother Nature. It's really like a speed run of evolution. You start with a big, random population of answers. Then you test their fitness. How well does each one actually solve the problem? The best ones, the fittest, get selected to be parents. Their traits are then combined or crossed over and sometimes randomly tweaked, that's mutation, to create a new generation of offspring. This new, hopefully slightly better, generation replaces the old one, and you just repeat the cycle over and over until an amazing solution emerges from the chaos. And that is the whole point. This evolutionary approach is built for problems that are just insanely huge and complex. Problems where other search methods would get hopelessly lost. Think about designing a more fuel-efficient jet engine, or finding the optimal trading strategy in a chaotic financial market. There's no simple A to B path. You have to explore a vast landscape of possibilities. And that's exactly what genetic algorithms were born to do. So there you have it. We've gone from an AI that's just blindly fumbling in a maze to one that can navigate with a compass, to another that can outplay a chess grandmaster, and finally to an intelligence that actually mimics the process of evolution itself. It's this incredible journey from simple brute force to creative problem solving, which, of course, leaves us with one giant question. Now that we have these powerful tools, what's the next unsolvable problem we should point them at?